So today lesson two, I want us to understand the concept of 3D or three-dimensional diagrams or schematic presentations. Okay, so I have on my screen a box. Okay, so um at each or at every point we can locate a specific values there. Okay, so in case let's say I am at, let's say, this point P. So the blue ink here is my starting point. Okay. If I want to come to this place, I can move on the x axis, and then I move on the y axis, and then finally on the z axis. Okay. So the same thing. Let's say when I'm um um at this place, I can decide to pass here or move on the y-axis as a certain unit, then also move on the z-axis. So it means that we are going to have both the y and the z, okay, but no direction to be taken for the x. So x is 0. Okay. Okay, so let's say if I'm also here and I want to come here, starting from here, one may decide to go on the z-axis and then go on the y-axis. And go on the x-axis. Okay, we are going to get x comma, because there is no direction on the y-axis, because when the person goes here and comes here, there's no direction for the y-axis, so it means the y-axis will be 0. So this is just a brief description of how you can locate points on a 3D form or a 3D shapes. Okay, so we can have point at every face or every edges. Okay, so it depends on how we traces to get our destination. Okay, so in case let's say someone too is here, it means the person can move on the x-axis and also move on the y-axis to finally get without moving on the z-axis. So the z part will be 0. Okay, so that is the whole idea. Okay, so I have also on my screen a term. Okay, so this also specify, or it is giving us a more information on 3D dimensions. Okay, 3D dimensions. Okay, so the thumb is pointing upward, and also the finger, this one too, is pointing on the x-axis, and the rest too that has been folded to is pointing on the y-axis. Okay, so it's like more like it is like it is in a three-dimensional space. So it is giving us the point how we can locate the x and the y and the z axis even naturally using our hand. Okay, so I also have on my screen some various types of angles that we can um, approach. Okay, so in case someone is going from this place to this place, we can approach this point from this angle perspective, from this angle perspective, or from this angle perspective. So irrespective of where the person or where we are moving our point to, we will get different angles. But for today's lessons, I want us to derive equations for the Cartesian coordinates and also for the spherical and cylindrical coordinates. Okay, so I have on my screen um, a graph representing both the x, y, z plane. Okay, so if the red ones are the x plane, and also the yellow ones are the z plane, and the y planes represent the blue ones. Okay, so we take a look clear to it. Okay, this one seems more clear. So let's start today with, so I have on my screen this diagram. Okay, so as I've indicated here, we have my x coordinates, my y coordinates, and my z coordinates. So now I want to derive the relationship between the Cartesian coordinates, which is the x, y, z, and then the cylindrical coordinates r, theta, z. Okay, so with this, in case let's say I'm choosing a point from this place, okay, so by tracing it downwards, I can make a small angle here. I can make an angle here from the x-axis, and that angle is called theta. And from the look of the diagram, we can see that the theta is alternating with this. Okay, so this and this part alternate. So it means the angle here is the same thing as the angle here. Okay, so with this idea, we can calculate for the or resolve both x and y onto the horizontal and the vertical component in terms of the angle they made with the x and y. Okay, so I have, you see, we know that this theta here is opposite to the line y. Okay, it is opposite to the line y and also adjacent to the line x. Remember, this is the line x. See, this one is parallel to this line x. So this angle theta is opposite to this line y and parallel to this line x. So I can draw my right angle triangle. So this is my angle, this is my angle theta. But the theta here is opposite to this line, and this line is the y-axis. So it means when I have my theta here, it's opposite to the y. So it means y should come here. And also, this theta too is adjacent to the x-axis. So adjacent to the x-axis. Okay. Then this one is the radius. Okay. This is the radius. Let me indicate it clearly. Let me use okay, so this part is the radius, that line. Okay, this line is the radius, so it means that the radius too is perpendicular, is perpendicular. Okay, because this angle is 90, this angle is 90, and the 90 faces the r. Okay, is the 90. So we can derive a relationship between theta and r and x. Okay, so we can boldly say that my cos theta is equal to x over r. So my x will be r cos theta. My sin theta too will be y over x. So my y will be r sin theta. So we can also say that from Pythagoras theorem, my radius square is equal to the sum of the adjacent and the opposite. So I'm going to get r squared to be equal to x squared plus y squared. And also the angle between them is tan theta is equal to y over x, which implies that the angle is equal to tan inverse of y over x. And remember, for the conversion from the coordinate axis to cylindrical coordinate system, the z is always the same. Okay, because there wouldn't be any change in the direction for the z, so the z will always remain the same. Okay, this only applies to when we are converting from a coordinate system to a cylindrical system. Z is the same. Okay, so thank you very much. I have some questions here and I will talk to it later.